Hello and welcome. In this video, today we'll introduce some common notation regarding sums, factorials, and binomial coefficients, and we'll also revisit the binomial formula, the generalized version of the binomial formula. So this is again part of the introduction. I'll just call this section notation. First thing I'd like to talk about is sums. Now for finite sums, there is a notation that many of you will probably be familiar with, but it might still be a good idea to briefly revisit that. So let's say we have a function that maps to our summons. So we'll have some function f that maps a finite set 1, 2, 3, 4, 5 up to some n to the real numbers. And just think of that as the summons of our sum. What we want to do is then the sum. We want to sum up f of 1 plus f of 2 plus f of 3 and so on up to f of n. This sum can be written as, and what we do is we use the capital sigma sign here. And then we sum up using an index, and this is this I here. So I is the sum index. We denote the upper and lower bounds for that. The lower bound is denoted here below the sigma sign. So this is 1 in this case. And the upper bound is denoted above the sigma sign. So n in this case. And then right next to that sigma sign, we just write the summand depending on I. So for a certain value of that index I, f of I is the summand. Yeah? So what that means is we start with the lower bound. We evaluate what is next to that sigma sign for the value 1 of I in this case, or the lower bound in general. So this is f of 1. Then we increase I by 1. We evaluate the next summand, so that would be f of 2, and so on. And we do this until we get to the upper bound, which is n in this case. So again, this I here, that is known as the summation index. This 1 here is the lower bound, and of course that doesn't have to be 1. And this n here is the upper bound. And again, that's pretty arbitrary. It just has to be higher than a lower bound, obviously. Okay, and there's one more convention that you should be aware of, and that is the empty sum. So if, for example, the lower bound is higher than the upper bound, so there are no summons in that sum actually, that is the empty sum. The empty sum, by convention, evaluates to 0. Okay, very brief example. Imagine something like the sum from 2 to 4 over I squared. That would be the following. We start at 2, and each summand is obtained by taking the square of the summation index. So this is 2 squared plus 3 squared plus 4 squared. Next, there's a very similar notation for products. Let me just briefly mention that. Similar to sums, you can do something like you want to take the product of a number of factors, like this, f of 1 times f of 2, and so on, times f of n. This can be abbreviated as, what we do here is we use a capital pi, and the same notation. There's an index, lower bound below that capital pi, upper bound above that capital pi, f of I. Quick example again. Let's say we have something like I from 1, 4, I plus 1. Then this would be 2 times 3 times 4 times 5, just like this. And again, there's a convention on the empty product. The idea is that an empty product should not change anything, as the empty sum does not change anything. Adding the empty sum to something doesn't change anything. Multiplying by the empty product shouldn't change anything. So the idea is the empty product is 1, because multiplying by 1 doesn't change anything. Multiplying by 0 would change quite a bit. Okay, so much about the product. Related to that is a common notation that is called the factorial. Again, the factorial is just an abbreviation for some number n in n0. We abbreviate by this notation n factorial. We abbreviate the product of I from 1 to n and just take I itself as the factors. So what this is this is 1 times 2 times 3 and so on up to n. Consistent with the convention for the empty product, we also define 0 factorial. That would yield the empty product because we have a product from 1 to 0. Obviously, there's no such factors. So by convention, that is 1. And you may know that factorial, that often comes up doing combinatorics. This n factorial is the number of permutations of n items. So the number of possibilities you have to arrange n items, different items. And factorial equals the number of permutations of n items. And finally, I'd like to talk about the binomial coefficients. So in this case, you have two natural numbers. So we have k and we have n, both natural numbers, with k less or equal to n, and maybe, or at least k may be 0 as well. We define the so-called binomial coefficient of n, choose k, written in this way here, pronounced n, choose k, or sometimes also n over k. That is defined as n factorial over k factorial times n minus k factorial. Or it can also say it's defined as 1 over k factorial times n times n minus 1 and so on times n minus k 1. So kind of the inverse of a factorial, if you want, this last part here. So that is n times n minus 1 and so on, and that's k factors here. Okay. And in combinatorics, again, this plays an important role. This n over k is the number of possibilities to choose k items out of a set of n items. Number of possibilities to choose k items out of a set of n items. And in connection with these binomial coefficients, you probably all know the binomial formula. And here's a general version of the binomial formula that says for real numbers x and y, we have x plus y to the power of n equal to the sum of k starting from 0 to n, and the summands are n choose k times x to the power of n minus k times y to the power of k. So this is the general case of the binomial formula. And you are probably familiar with a number of special cases, will appear very often. The most well-known is n equals 2, so x plus 2 squared, for example. What do you get here? We evaluate that sum, then we have 2 choose 0 times, but first we get x squared times y to the power of 0. Then we get 2 choose 1, x to the power of 1, y to the power of 1. And finally, if k is 2, we get 2 choose 2, x to the power of 0, y to the power of 2. Or written more concisely, what we have here is, well, 2 choose 0 is 1, so this is just x squared. 2 choose 1 is 2, so this is 2xy, and 2 choose 2 is again 1, so this is y squared. And of course, you also know the relation for x minus y, that works as well. You would write that as x plus minus y like this, and then apply the general formula. And if you do that, what you get is x squared minus 2xy plus y squared. I'd also like to mention the case of n equals 3, at least briefly. X plus y to the power of 3 will also appear sometimes. It's good to at least see that once. So if you apply the general formula here, you get x to the power of 3 plus 3x squared y plus 3xy squared plus y to the power of 3. Okay, and finally, one special case that you should also be aware of. 2 to the power of n. That could also be interpreted in terms of the binomial theorem as 1 plus 1 to the power of n. You can just apply that theorem. What you get is that sum n choose k from 0 to n, and then you get 1 to n minus k times 1 to the power of k, so this is always 1. So 2 to the n is the sum over all these binomial coefficients. Now that's at least nice to know. Okay, that concludes our little video about sum notation. That almost concludes the introduction. We'll have one more point we're going to cover. That's going to be an introduction to mathematical induction in one of the upcoming videos. I'll see you then.